qualitative work which has been done together with Juan Pablo Ortega, who is present here, and also with Professor Luke Bowens from UNLEN. So, what we are going to talk about, I will give you some preliminaries and some motivations why we're doing this, what for, what is motivation behind all these problems. Then I will give you some introduction, general one, to multivariate covariance and correlation models. And then I'm going to give you some details on our work, our paper that is devoted to the estimation methods for multivariate correlation models. In particular, dynamical conditional correlation model, DCC. And then I will give you some empirical performance results. So, well, maybe for some of you is already well-known facts. I'm going to just give you some notation. So, let PIT will be denoting the price of the asset I at the moment of time t, at the date t. Then we have one period returns that we are going to work with. This is RIT. Whenever I put the bold symbol, this means vector. Whenever it's a big Latin letter, it's going to be always matrices. And what are the frequencies of such return series? In general, we have these three main types of frequencies that one can work with. So we have so-called low frequency. This is a frequency lower than weekly. So for example, monthly. Then we have so-called high frequency. So it's going to be from weekly to daily. And we have also ultra high. So it's going to be higher than daily. It can be intra-daily, whatever. So what is the market volatility? So what is the rationale behind why we really do what we do and why we're interested in volatility itself? So the main topic, I would say, of financial econometrics in a whole is how to define, specify, and what is important, measure volatility of asset returns. So volatility is, of course, a quantitative measure of reliability of our asset returns, and also there is some kind of so-called double uncertainty in financial markets about volatility. So we have uncertainty about returns and about the instantaneous volatility of returns. So our main goal, or I would say the topic of financial econometrics, is somehow to try to measure this volatility in some indirect way through observations of our asset returns of a given frequency. So, what can be such a measure? The measure can be model-free or model-based. So we can work with the sample-based measures and also on the model-based. So, what are the main sample-based measures of instantaneous volatility that one can use? Is the so-called historical volatility. So how it is done? We choose some rolling window of the length, let's say capital M, and we just use the covariance matrix HT. Here is with a subscript M because this is rolling window M, and we just take the sample estimate for such covariance matrix, and this is what we're going to use as the proxy for our squared volatility, so to say. And then we have also the realized volatility that usually is measured like we are taking some intraday daily observations of our asset returns, and then we just construct our HT, let's call it D, as just this relation. So this is going to be a realized volatility, and also one third way of estimation, the proxies for volatility. It can be also taking the absolute value of our asset returns and then. So another approach that we would like to follow and we believe to be much better is so-called model-based volatility. So we are not using just the sample-based estimates for our covariance matrices, but we believe that the model can give us much more information about the dynamics behind. So what are these models? Risk matrix, mainly multivariate Garchi models of different kinds, where we have some innovations XIT distributed with a covariance matrix, let's say identity with mean 0, normally distributed. We have also some group of multivariate stochastic volatility models. And what is the main about these models? So in these models, we always have the case when our HT So each type of these models, it always specifies HT, our conditional covariance matrix, as some parametric function of the past observations, and also the lag values of our HT. And also, given the relevant information and the estimate of the parameters that are incorporated in this model, we suggest that the prediction is feasible. So, what are the constraints that go with this approach? So, of course, we have to pay somehow for the chance to be able to use the models. So usually this payoff comes with the constraints. So what kind of constraints we usually have to deal with is usually stationary constraints and positivity, or let's say positive semi-definiteness constraints that involve the model parameters of the given shape. So what are the examples? So one, for example, in practice in banks, in some institutions, usually these three types of volatility estimates are used in real life. Because as you see, well, for anybody looking with a bold eye, just looking at these three plots that are given by just absolute returns, taking as the proxy for volatility, then we have the model-based approach, Garch volatility, and the rolling window volatility, or historical one, which I just showed you. So one can see that they are somehow resembling each other. What is another thing which is crucial here is that actually the model-based approach, or whatever approach we are considering, is very closely connected to the frequency that we are working with. So actually for Garch models we have to be very careful what kind of frequencies we are choosing working with our asset returns. So what is usually done when we are working just with sample-based measures? So what is done is that we take actually the covariance matrix of our asset returns with some rolling window M, and we just assume that forecasting is done with exactly the same value of our covariance matrix, which of course is not that good, because depending on our forecasting horizon, it's somehow not reasonable to assume that the value of our covariance matrix, conditional one, will be the same as, for example, at the moment time t. So another approach is to use the model for constructing the forecast. So we are not taking anymore, we are not assuming that this is going to be exactly the same value at the time t plus h. We're using some model, but based on time series, right, from some moments of time between this value of our rolling window up to some t. And we can also use some models with the assumptions of other than normal types of distributions. So here you can see the list of works you can be interested in. So later on I can give you a presentation so that anyone who is interested in further reading can get acquainted. So what is the application of our multivariate volatility model? So first of all is, of course, portfolio construction, allocation management. Then value at risk measurement. And also this work is also something extremely helpful for those who may want go into further reading, because it's a very nice survey on multivariate Garch models. So how do we deal with portfolios? So it's a usual setup. We have the net return T at some moment of time t. We have some portfolio with weight vector WT. As I said, always whenever I put bold character, it's going to be always vectors for us. So we have n assets, and is dimension of our weight vector, and we have some net return PT, which is just multiplication of our weight vector with the net return ZT. And we have the conditional variance at the moment of time t, which is given by this relation, nothing new. So what kind of two portfolios? These are the two portfolios, two kinds of portfolios that we are going to use in our empirical part. So it's going to be the minimum variance portfolio, which is given by actually solving the optimization problem, and the equally weighted portfolio, which is going to have always 1 divided by n, depending on the number of the assets weighted. So value at risk, again. So this is one of the applications of these models. So we would like to have a value of our bar. So yeah, it's a quantitative measure that is measuring the risk which is associated to keeping the portfolio. And so the bank holding a portfolio, of course, incurs some risk of losses, and depending on some horizon. So according to Basel banking regulations, we need to come up with some measurements for this VaR, which doesn't have to go over some prescribed value, right? So in this case, what are the approaches to measure the VaR? We can actually just take the alpha percent left quantile of our distribution of our returns. Or, for example, if we know that we have some model behind, we can use some information taken from this model in order to come up with the value of our VaR. So, and of course it helps to diversify the portfolio. By example, we can always say what is the VaR associated to the probability given by the confidence level alpha, and taking the distribution of our assets. So, univariate VaR modeling. As I told you, we can come up with some univariate model. We can come up with some estimate of our VaR. And but what is bad about that? We know that our assets can be of any dimension. Let's say some fixed dimension n. And when we are working with a univariate approach, it's directly dependent on the portfolio allocation at the moment time t. And requires, of course, repeating each time the volatility modeling every moment of time t if we want to measure it on some different t. So, and of course, it's not that good, it's not very convenient for risk measurement. Because, well, it's strongly dependent on the moment of time when we allocate the portfolio. So, what we would like to put forward in this context is the use of multivariate Garch models that we believe are performing much better in this setup, and also can be applied in the tasks I just mentioned. So what we just take a general setup. We are working with an n-dimensional conditionally characteristic discrete time process RT, which RT will denote for us asset returns. And we have a usual setup, as I just showed you. So what we have to keep in mind that in this case we have HT, which is a predictable positive semi-definite matrix process. And for each T, we have the random matrix given at this moment of time. T is F T minus 1 matrix. So why we talk about the variety of families for these multivariate Garch models? Because actually, depending on the way we would like to describe the dynamics that goes with this matrix process, depending on that, we can choose that or another model. We can construct that or another model. So, models that specify these conditional covariances that we just talked about, and the various variances as the functions of their lagged values, as I told you before, and the values of the return time series. This is going to be the multivariate generalization of the usual Garch 1-1 models that you maybe already have some acquaintance with. So there is a whole zoo of such families of models. So there are VEC Garch, DVEC, BKK, factor Garch, many models. And also there is another group that actually specifies our conditional variances and covariances using the information about the conditional correlations. And this is our main, so to say, focus of our work. So if you want, we always work with this kind of group, and namely where the results that I am going to present you, they go with this family of models, which is called DCC, or dynamical conditional correlation models. So what is the group of models? So I'm going to tell you just briefly in few words what variety of models we have for the first group and what variety of models we have for the second group, so that you can see what is the difference between these two. So first of all, I would like to tell you what is the VEC operator. So if you want, the VEC operator does nothing but given some metrics of the dimension n by m, it just sticks all the values in the vector, and this is how we get the action of these operators. So then we have also VecH and MatH operators. So for all these operators, we always have the inverse. And sometimes we would need the adjoint operators. So for VecH is a little bit better for our setup because any model we are working with, it always deals with the covariance matrices, conditional covariance matrices or conditional correlation matrices. So these matrices are symmetric. So in order to try to construct the model for such matrix processes and also to come up with the parameters for these models, the only information that we actually need is just the lower triangular part of our matrix, including the main diagonal, because obviously the upper part will be symmetric. So this VecH operator, it just sticks again all the elements on the main diagonal and below it into the vector. So nothing more. And MatH is just the inverse. Given some vector, we can construct a symmetric model. So how it is used for Vec-Garch models? Well, if we have some order of Vec model, let's say Q and P, we can say that, okay, we can write our conditional covariance matrix process in a form which is given in this relation, where we have some set of parameters A and B, and also we work, as I told you, only with the VecH result of the operator. So we are working always with the vectors that contain only the lower triangular part of our symmetric matrix with the main diagonal. So here the dimension, as you see, given that the number of the assets is big enough, we already work in the dimension big N. So, okay, in order to estimate the parameters of these models, it's already not that easy task. And plus to that, we have some constraints that we have all the time keep in mind when we are trying to estimate these kinds of models. So we have the stationary constraints where we demand this relation, the resulting matrix to be positive semi-definite, and also we demand that this MatH operator, as I told you, this is the inverse of our VecH operator of these parameters, always gives us something positive semi-definite or definite. So this, if you want to set up, is something that we used in this current work, because this is something that Juan Pablo with Stéphane Chrétien, they did in 2013 in their paper, where they suggested an estimation method that can be used for these kind of models in the higher dimensions. So they managed to go up to N8, which is already quite something, because if you just count the dimensionality of such a problem, you can see that we are stuck with the problem of such called the curse of dimensionality. So this method that I'm going to give you some more details about, it was actually very successfully used in this setup, and this is something that we generalized and used in the scope of DCC models. So what other models can be? Well, there are many different models. So what is the main concern behind trying to come up with different models for such conditional covariance matrices? Is actually try to avoid, at the same time, to come up with nice parameterization, in the meaning that we would like the number of parameters, the dimensionality of our parameters to be as small as possible, so that the estimation is feasible, and at the same time, somehow to get rid of, at least of the part of the constraints that we have. Because otherwise we have to deal always with the constraint optimization, which is highly non-trivial. So what are other ways to go about it? Well, actually what we'll do, for example, in the BKK model, which is something that you may find a lot in the literature, is trying to come up with the parameters of these models that automatically ensure the positive semi-definiteness of our H10. So in this case, we have only stationary constraints that kind of are supposed to give us something easier and more feasible, but actually on the practice is also non-trivial task to be able to estimate these parameters. So what is another group? So I didn't give you all other, there are many, I gave you the survey. You can just look at the survey and you will have all these list of different multivariate conditional covariance models of the Garch type, so-called M-Garch. And now we go to another group of models, which is something that is in the focus of our study. So this is so-called conditional correlation models. So as I told you before, now we are trying somehow to get knowledge about the dynamics of our conditional covariance matrix from the knowledge of the dynamics behind the conditional correlation matrix process. So in this case, we have the same setup. So actually, the construction and also the estimation of these models is constructed from two stages. On the first stage, we are just coming up with a Garch model for conditional variances for each number of the asset I. So it's going to be always univariate. For the given number of our asset, we come up with a Garch model, and this way, this is something extremely easy to do because we have simple constraints on our alphas and beta parameters in the Garch model. And now, having knowledge about these conditional variances, we can actually construct the so-called standardized returns. For every number of the asset I and every moment of t, we can come up with these standardized returns. And now we forget about the initial asset returns and we keep working always with the standardized returns. So it's easy to get because you are given the asset return, you are given sigma that you just obtained out of the knowledge of conditional variances for the Garch model, and you come up with these factors. So, what is the second stage? On the second stage, and this is at the core of all these conditional correlation models, we write down the relation that allows us, from the knowledge of our RT, which is going to be the conditional correlation matrix process, to inherit the knowledge about the dynamics behind HT. So how it is done? Well, sigmas, we already know them because they come from Garch models, univariate ones. So to construct these diagonal matrices, we already have them. So on the second stage, what we're interested in is actually what is the model that goes with our RTs. And this is from this step, actually, this is the main thing about the dynamical correlation models. Since we're not interested anymore in HT as it is, we forget about our diagonal matrices, which are already obtained out of the first stage. And now, all we have to do in order to construct this model and also to estimate the parameters is only to come up with a model for RT and to be able to estimate its parameters. So, what is the simplest thing you can imagine, even though it's widely used? It's just to assume that our RT is just constant. So in this case, there is no model behind, no constraints. It's extremely easy. We can get the information about RT just using sample-based estimates. And this is how we get all the elements of our HT. So, well, even though this looks extremely simple, the assumptions behind about the constant character of our RT are extremely not reasonable. Because actually, what we do, we're trying to come up with some way to describe the dynamics behind our conditional covariance matrix process. But at the same time, we assume that our conditional correlations are just constant. So what's the point of using the model in this case? Well, these CCC models are used a lot in practice. So what is another? So this I just give you a short slide and about other ways to come up with a model for RT. So you see there is so-called the TVC model. So as you see, there are from easy to write down and to construct models to something like this TVC model. But again, what is good about this is that stationarity constraints and positive semi-definite constraints are extremely easy. So in this case, the constraint optimization problem will be much more feasible. So now I approach to what we are working with. So we are working with so-called DCC models, as I already mentioned. So in the most general setup, as you may think of, this is so-called, this is written down as a so-called Adamart DCC model. So what do we have in here? So we have our RT, which is written down in this relation. This gives us the conditional correlation process, which is modeled in the following way. So what we're here interested in is a QT. Why? Because QT star are obtained just as the diagonal matrix is taking the diagonal elements of our QT and just taking the square root. Why we do that? In order that in the end we get the conditional correlation matrix with the ones on the diagonal. So now we forget about everything that has happened before and we start looking at the model which is written in this 13 relation. So this is, when we are talking about the DCC model in the general setup, this is what we actually mean. So now we would like to work with this kind of model, which is very similar if you forget about the fact that this actually is just gives you the constant, because it implies, it involves only the parameters of your model, and also the S, which here you see that can be just estimated by the so-called approximate targeting procedure out of the sample-based covariance. And here what we have is just we forget about this. This is just the constant. Now we look that actually this model resembles a lot the Garch models. So we have our parameters A and B that in general are just symmetric matrices, and I denote just the vector of ones. So S, as I told you, it can be estimated beforehand. So now what we would like to be able to do is actually to estimate the parameters that go in this model, so A and B. So what are the constraints that go with this model, and why estimation of these parameters becomes so interesting? Is actually the fact that we have these stationarity constraints and the positivity constraints that guarantee that our process will be stationary, and actually it will guarantee that our QT that we obtain will be something positive semi-definite, which in its turn will give us nice R, and also HT that will be also positive definite. So now we need to work with this model, and as you see, it involves the constraints that are extremely difficult to tackle at the time of the estimation of the parameters, because we require that these matrices are positive semi-definite, and also we require the positive definiteness of these matrices. So, well, and stationarity constraints is just the absolute value of our sums of the corresponding elements. Yeah, I forgot to tell you that actually why it's Hadamard, because here this means the Hadamard product is the element-wise product between the matrices. So, as I told you before when I was showing you the Beck model for the conditional covariances, so Beck-Garch model, I was telling you that actually there are some ways not to work with the full matrices as soon as we know that they are, for example, symmetric. So there are some ways to reparameterize our parameters, our matrix parameters in our model, so that the dimension of the parameter space is reduced somehow, and that we have to estimate smaller number of parameters in the end. So for that we have different parameterizations that I'm going to show you, and also we have some estimation algorithm, and also in the end I will give you some performance here. So these are actually the models that we are working with in our paper. So the scalar DCC, you're going to see in 1 minute what is that. But actually this is the simplest model possible in the setup of DCC. And we are working with the Hadamard, so-called full rank DCC models, as I just showed you, the most general one. Then we're working with the rank deficient and the Allman and so-called Allman shuffle. These two models we introduced. So, again, coming back to our Hadamard DCC model. As I told you, if we look at the general setup for our Hadamard DCC, we notice that actually our parameters A and B are symmetric. So is of course QT, and therefore what we can do actually, we can use the same approach that was used in the Beck models. So what we would like to be able to do is having some vector to be able with that vector to give all the information about the parameter matrix itself. So how it is done, we have mat-h operator that I showed you a few slides before, which actually takes some vectors of some given dimension n, where n is defined through this relation, knowing that the n is the number of our asset recurrence. And actually you can rewrite the same model. Here nothing changes, but just using the fact that our matrices A and B are symmetric. So in this case, what we were hoping for is that our stationarity constraints come down to only n constraints, and actually positivity constraints are the same, but just using our operators language. So, scalar DCC. So anywhere where you would find DCC models, anywhere in the literature, when people mean DCC model, it's always scalar DCC. So I'm going to give you the setup, and I would like to deliver somehow why this model we believe to be not that good. So that's why the title of the talk is non-scalar models. So now, what assumption, the simplest possible, we can have as far as our parameter matrices are concerned, is the fact that we have just two numbers, A and B scalars, and our parameter matrices are just obtained as one scalar multiplied the matrix full of ones, right? So in this case, how this model will be written is actually just taking these parameters A and B and rewriting the same model. So what it wants is obvious. Obvious is the presence of extremely easy to tackle constraints, right? We don't work anymore with matrices, we don't have any more high dimensions, we just have simple constraints like we had for the Garch model. So that actually involve only the scalar parameters. So of course, in this case, the estimation is extremely easy to provide, and that is why these models are so widely used. So if you would think of the other marked setup that I showed you, there the problem is much more difficult to tackle, and that's why there are non-estimation methods present in the literature that allow to estimate those parameters. So if you want, scalar DCC is the only one that in the literature are given as the ones that can be estimated. So what is another group that we are also using in our paper is so-called rank deficient. So in this case, we assume that our matrix parameters, so parameter matrices A and B, are actually rank deficient with a prescribed rank. We assume that the rank is common for both. Let's say rank is equal to 1. And in this case, we can actually write down these parameter matrices in the following way. And in this case, what we are interested in is the fact that our A and B can be obtained out of the intrinsic parameters small a and b, which are just vectors of dimension n, where n is the number of our asset returns. So in this case, we have something at the same time easier, because as you see in the positivity constraints, we don't require anymore the positive semi-definiteness of our matrix parameters A and B, because by construction they are. So our positivity constraints are reduced to just one relation. But at the same time, we have identification constraints that in our paper we find the way to go about, because actually not having these identification constraints, we can have actually many vectors A and B not properly identified that will give us the same value of our QT and the same value of our parameters. So what we use in order to come up with the model construction for that, we introduce some operator that we call it Matar operator, that takes just the vectors of the prescribed dimension and star, where knowing the rank of our parameter matrices and knowing the number of the assets, we can easily find. So what this operator, it just takes the vector in this R and star, and it gives us the rectangular matrices that contain all the zeros above the diagonal, and also give us the prescribed size n by r. And as we mentioned before, our identification constraints will involve the positivity of the first element standing in the first row of our matrices. So we have also the inverse of this operator. We have the adjoints for these operators, because later on what we will need is to come up with a gradient of our log likelihood function in order to be able to provide the estimation of the parameters. So in the case when we have the rank bigger than 1, this is where we would need these operators mod r and vec r, because in this case this is the same, but rewriting the same model with a different parameterization, that's all. The only thing that we have to keep in mind that now our A tilde are not anymore vectors, these are some rectangular matrices, that's all, of a prescribed rank. So, and in this case, again, as you see, the positivity constraints are easier, because again, by construction, our A and B will be positive semi-definite, and in this case, we have stationarity constraints and identification constraints that I was telling you about. So actually, we demand that all the elements that are situated on the diagonal are always positive. And this is what we are going to use in our constraint optimization. And now go to models that we introduced. So this is the Allman DCC model and so-called Allman shuffle, which is just some kind of modification of Allman DCC. So for those of you who have somewhere met in the literature, there is such a group of models which is called Midas models. So these models that are usually used in the macroeconomics, they involve, they take the use of so-called Allman function. So what is this function? I'm going to give you the profile just in a second. So actually what it does, in this model, what we assume is that our matrices are of rank 1. So this is a particular case of our rank deficient 1 models. And we write down them, these A tilde and B tilde vectors as you have here. We write them down as the operator, the result of the action of the operator Allman n on the just vectors in R3. Because Allman functions, these are some functions, they take always 3 arguments and give us the value. So in this case, what we need is just 3 parameters in order to parameterize the whole parameter matrices big A and big B that we have in our DCC models. So if you want, this is some kind of trade-off between having many parameters, like we had in the Adamart case, or just usual rank deficient case, and between the scalar model. Because here, what we need is just, 6 parameters in order to come up with a model. So, while for scalar we have 2. So, what we would like to see is that suggesting the estimation method that is able to give us the estimation for all the parameters, for all these kind of varieties of models, we would like to be able to compare the empirical performance of these models in order to be able to say, so actually using the scalar model, despite its convenience, is it reasonable or not? So, what is the element-like operator? So actually this is just the operator that, as you see, gives our vector A tilde and B tilde some exponential profile. So in order to illustrate for you what is the difference between, for example, scalar, rank deficient 1, and the particular case of the rank deficient 1 with Allman model, here you have 30 assets, right? So here you have, in the scalar case, sure enough, since we are modeling with just one scalar number A, so this is, if I'm not mistaken, this is, yes, the values are small, so it's always for A part. So here you have, in the scalar case, as I told you, we have just one number. So no matter how many assets we have, we estimate these parameters, with this parameter just 1, and it gives us the value for each asset. We will have just one number, right? For the rank deficient one, we have all these 30 people will be actually different because it's going to be just the vector of the length 30. So for the rank deficient, as you see, our A and B are always of dimension n, which is the number of our assets. So if you want, this A is given here by this profile. What the Allman operator does, it actually tries to find the trade-off between these two setups in order to have at the same time some profile that takes into account the fact of the what is the magnitude of our correlations, and at the same time it tries to parameterize our parameters big matrices A and B with some small number of parameters. So in this case, you see that the red line is our vector A tilde, right, which is obtained at the action of our. So, the Ullmann shuffle, I'm not going to stop in detail on this, but actually the only thing that we do here is kind of engineering trick, because if you look at this profile of this function, we have to, it's strongly dependent on the number of our assets. So depending on the way how we arrange the numbers of our assets, this profile will be different. So what we would like to do is not to have the dependence that takes into account just our choice of the ordering of the assets, but to have this ordering somehow explained. Why we take this ordering but not something different. So what we do, we just rearrange these assets, doing just a principal component analysis, arranging them according to the magnitude of the projection on the first principal component. And this way we get a new ordering, and this is where we can work with this exponential profile effectively. So now, I give you some conclusion about the models that we use in our paper. So it's going to be the Adamort model, as I gave you before. So as you see here, we work with this dimension big N, which is taking n number of the assets big enough. It's obvious that we have many parameters to estimate. The scalar one, where we have just two parameters to estimate, right? Two scalar values, and that's all. And this we're going to use as a benchmark for all other models. And now we have rank 1, so you have rank 2 and Ullmann models. So you have the whole zoo of different models. And now what is our goal? Our goal is that for scalar model we know how to estimate the parameters because it's extremely easy to do. Plus we have the extremely easy to tackle the constraints for these models. But we have nothing available for estimation of these models. So how can we draw some conclusion about if using a scalar model is better or not, despite its simplicity? So here I give you one more illustration of how these models are arranged. So this is an inclusion diagram, if you want. So the Adamort is the most general case. Here you have the particular cases of our rank deficient 1 models. Here in the middle is with rank 2, obviously, and the simplest one is the scale. So when I'm talking about the big number of parameters, what do I mean? So here you have the table that just gives you some feeling about how many parameters we would finally have to estimate. For the Adamort case, that is the most richest one. So we suppose that we have the richest model that gives us a lot of parameters, and we will be able somehow to inherit the dynamics of the process if it's difficult out of this model the best. So given the number of the assets 30, we already have 930 parameters to be able to estimate, right? In the scalar case we have 2, and we have other cases in the middle. So even if we had some means to estimate the parameters of these models, knowledge about how many parameters we have and how rich these models are gives us no information about how these models will be good in the forecasting, for example, or any of the applications that I just showed you before in the beginning of the presentation. So, how do we do the estimation? The estimation we do using just a quasi-log likelihood function. So we come up with our function. Here it is, nothing new here. So the only thing that we use here is the same notation as I showed you before in the previous slides. So here you saw the RT. Here we just use the fact that our RT is constructed of our Q matrix. And the models of this QT, I just showed you the variety of these different models. So as I told you, we have 2 steps, 2 stages. We can estimate first our Garch parameters. We forget about them because they are common for all the models. And now we go to the second stage, and this is where we're gonna estimate our parameter matrices A and B, right? Or depending on the parameterization, the vectors or the scalars that give us those parameters. So in this case, we are aiming at maximizing likelihood with respect to these parameters, right? this theta A and theta B will denote for us, for every given type of model, some kind of intrinsic parameterization that we just chose, right? It's going to be some vectors in R, whatever dimension is working for this kind of models, or in the scalar setup, just two scalars. So what we do in our paper? So we are working with a constraint optimization, right? So in this case, we would like to minimize minus log likelihood or maximize log likelihood, doesn't matter. And further on, in further slides, keep in mind that this we're gonna denote as just f of theta, not to drag all this log likelihood with us. So what we have? We have these common parameters that come from the first stage, which are common for all the models, right? We forget about them. And what we're interested in is how this log likelihood function depends on these parameters in order to come up with a gradient of this log likelihood. And of course, we will be able to estimate the parameters. So, and again, we extend the optimization method that I told you was so performant in the Vec-Garch models, and we're trying to see that how performant it will be in this case, whether we can generalize it. We managed to do that, and we put it to work for these models in order to see what model among these can be more performant. So, if you want here, well, here I'm not going to stop by in detail, but what we have to keep in mind that actually we can write down explicitly the gradient of our log likelihood function for every given model that we consider in our paper. So we can come up with explicit formulation. So knowing the gradient of our log likelihood function, we can also write it down in some iterative form so that we can somehow implement it in whatever code we would like to obtain. So in our numeric scheme somehow. So we can do it. And now the main question, well, it's not the main question, but it's extremely important, how to tackle the constraints that we have for all these models. So we know that these constraints, for example, in the Ullmann case, there are nonlinear constraints. These are positive semi-definite constraints, so we have somehow to control our eigenvalues of our matrices at the time of doing the optimization, right? How to do that? So we use so-called family of relaxation methods. So one of these methods is introduced by Bregman, is so-called Bregman divergence. So what we have to keep in mind that you can come up with many functions that actually are can be called as Bregman divergences. So all in general setup is going to be something like this. So we have to keep in mind that our function is strictly convex, differentiable, and that actually this will give us the so-called Bregman matrix nearness measure. So why do we need this? We would like to have something that will immediately blow up for the function for us as soon as we approach to the parameter subspace where the constraints are violated at the time of running the optimization, so that we don't have to come up with a dual problem and so on. So we work with the so-called Berg divergence, which is given by something like this for the metrics involving constraints. And in the linear and nonlinear setups, we also have some ways to come up with the explicit formulation of these divergences, right? So what is going to be our optimization problem in the end when we have our Bregman divergences? So you come up with your f at every step k, right? As just the sum of the usual terms that you might have, right? The Hessian and so on, the value of our function at the given iteration. And we have actually this part, so this is in Hessian, so in this part we have the divergence coming into play. So actually, this is how we're going to work with the primal, not going to dual, and this is how we're going to take use of the information that this divergence has to blow up as soon as the constraints are violated. So, if you want just a simple plot in this case, so what people usually do is they, for example, you can think of taking the Frobenius distance, right, as some kind of Bregman divergence, but it's not good for our problem, because it doesn't give us what we want, because Well, assume that we are working with some function. Well, here was the general setup. So we are interested in all the parameters A, which are positive definite, right? That will minimize for us the value of this function. So let's say we have this function. So what is the difference? So in this case, this is the case that we are working with. As soon, so let's say we are always interested in the parameters that are positive semi-definite. So in this case, we would like to have something, some so-called penalized local model, right? That would give us this, that will go to infinity in the points where you approach the subspace of parameter subspace where the constraints are violated. So as soon as you approach it, we would like it to blow up so that this iteration is not kept and we go back to the previous iteration. In the Frobenius case, as you see, it doesn't give us what we want because as soon as you approach here, you may find yourself here. So in this case, this is not what we want. We would like to have some local model that would control itself the fact that the constraints are not violated. So we have the explicit way to write down these constraints, right, involving these divergences for any type of the constraints. So we group them, well, in three basic groups. So we have our semi-definite or definite constraints that involve matrices, parameter matrices. We have our nonlinear positivity constraints, like for example in the case of Ullmann, and of course the linear positivity constraints. This is easy. For example, for scalar model. So what we have to know is that actually for any of these models that I listed, we can come up with the explicit way to write it down. So we can always write down our optimization problem in the following way, where we have the group of our our positive semi-definite definite constraints, the group of nonlinear constraints, and the linear. So if our model has a few groups of constraints, we can incorporate them and put it to work. So we can come up, of course, as I told you, with a gradient of local model, because the gradient of the log likelihood function we have for any specific model, and we can come up with the gradients for all these divergences explicitly. So it's a lot of work, but it can be done, it's computationally feasible. So we come up, here are the gradients that involve some adjoint operators, depending on the MAT-H, ALM operators that we work with. So in the end, we will need also the Jacobian of our local model. So you see, I'm not giving the explicit formulation for any given model, but actually it can be done. We have it. And now, having a method of estimating all these models, we can actually put it to work in order to decide what is the empirical performance of these models. So our main thing is to draw some conclusions, whether one has to use easy to use scalar models and extremely fast to estimate in order to apply for some practical tasks, an empirical study, or to work with the richer models, right? Much richer, parameterized, with more parameters, as soon as we can estimate them, as we just showed. So now we can estimate. So we use two periods. So what is the difference between these two periods? The first incorporates the crisis events in the in-sample period, and out of sample we're post-crisis, right? So actually, yeah. And then the second one, it has the crisis in the forecasting period. So we have before crisis, right, events in our estimation period. In the out of sample part, we use already the crisis events, so that we give some information about these two tasks, right? Because whenever you put one period to another, you will always get the question, why didn't you use the crisis events in the forecasting period, which is much more difficult, for example, but only in the estimation. So what is our data set setup? So we take this data set and we also come up with so-called CAP model, which is actually what it takes is that we take into account the fact that also these asset returns dynamics is driven somehow commonly by, for example, in this case, SP500 index. So we get rid of this, we're filtering that component out, And later on, we are working with our asset returns that are obtained as the result of the preceding regression. So we did it with CAPM and without CAPM, so actually nothing really here changes. So in both cases, we get something consistent, which we're happy about, because actually there are many works that involve this CAPM and not. So actually there is no difference. And now, well, this part I will try to go fast, because actually these are a whole set of statistical tests that we just programmed and ran in order to come up with some comparison, which models are better, which models are not. So as you see, well, both in the in-sample and out-of-sample cases, we can draw some information about which model is the best. So what we would like to see is that actually in the in-sample case, the richer model you have, the better fit you have. So that's why the other mark, the most general one with the more parameters, has to be more performant, right? Which doesn't hold for the out-of-sample period. So that's why with these ASCLR tests, here I show you there's some problems with these kind of models, DCC models, that there is some bias present for both estimates of A and estimates of B, which come up with the type of model. So actually this doesn't come up from our estimation, it's just a feature of these models. And that's why now we are trying to put this method to work with other kinds of models, which don't have this problem of presence of bias. So here you see that for parameters B, it always grows the values with the dimensions, and for parameters A, we always have something that goes actually to 0 with the growing dimension. So in our empirical study, we took just 30 assets. We just show that it can work up to dimension 30. And yes, one method that we also, well, there are many tests that we conducted. We left not all of them in our paper. So one method that we like is so-called model confidence set test statistical, so which I show you the results. So actually what it does, given some confidence level, it selects the subset of the models that are assumed to be equally performing, right? So as we see, so in the situation of the first period, so actually what we see is that up to some dimension, the scalar model does pretty well. But when the dimension grows, actually this is the almond group that starts performing better. So this information is useful for us because actually this gives you some rationale why not to use scalar models that are so easy to be estimated. And for the second period, you can see that actually scalar model is not that performing even in low dimensions, but actually the almond shuffle does pretty good together with the almond with the growing dimensions. So main findings. So we were able to construct the estimation method that gives easy to use tool in order to estimate the parameters of all these models. And then we write it down all explicitly, we give you some results, and also in the end we construct the empirical performance tests. And we draw the conclusion that actually non-scalar DCC subjected to all these constraints that I showed you are feasible to tackle in dimensions up to 30, and even more. We tried for 40, I think, the most. So one has to be extremely careful with having the data set, what model to use. But actually having these tools, you can select any model you want, which is performing better, and to use that kind of model, but not just scalar one, the most silly one among the one. So what we are now actually, we are finishing our paper, and this is what I wanted to present. It's a pity that yeah, I could not, well, with some problems of the date for presentation. But actually now we are finishing the results. We applied these tools, of the optimization tools, for so-called DVAC models. And we also put to work the composite maximum likelihood estimation for these models. That gives us the chance to somehow reduce the number of parameters for all these models that I just described, just based on the fact that we are working with sub-models, dividing our log likelihood estimation problem into some composite log likelihood estimation. So, and we are now finishing this part of work, and we can show there that actually this problem of presence of bias is not that evident anymore. It's not that present for these kind of models, and they perform even better than what I just showed you. So, thank you.